NEC section 240.4b addresses the use of overcurrent devices in relation to conductor ampacity. This section states that where the ampacity of a conductor is determined by tables 310.16 through 310.19, or by the provisions of 310.22 through 310.50, an overcurrent device rated in excess of the ampacity of the conductor is permitted to protect the conductor under specific conditions. One of these conditions is for conductors whose ampacity is determined by table 310.16. The next higher standard overcurrent device rating is permitted where the ampacity of the conductor does not correspond with the standard device rating. To apply this, consider a scenario where the conductor ampacity is 180 amps at 75 degrees Celsius, given that the circuit breaker lugs are rated for 75 degrees Celsius. A standard circuit breaker rating is 200 amps. According to section 240.4b, it is permitted to use the next higher standard overcurrent device rating, which is 200 amps, because the conductor ampacity does not correspond with the standard device rating of 175 amps. The 200 amp overcurrent device is acceptable. It is important to understand why an inspector might question this. The inspector might be concerned about the potential overcurrent protection provided by the 200 amp circuit breaker. When the conductor is rated at 90 degrees Celsius, its ampacity is 205 amps, which is slightly higher than the 200 amp circuit breaker rating. However, this falls within the allowable overcurrent protection limit permitted by NEC section 240.4b. This section allows for a certain degree of overcurrent protection above the conductor's rated ampacity to accommodate standard breaker sizes. If faced with such a situation, it is advisable to discuss concerns with the inspector. Explain the rationale behind the installation, providing references to the relevant NEC sections to support the decision. If necessary, contacting the local authority having jurisdiction, also known as HA, is an option for clarification on the code interpretation. Remember that the HA has the final say in interpreting and enforcing the electrical code in their jurisdiction. Always prioritize safety and compliance with the NEC when designing and installing electrical systems. When selecting conductors and overcurrent protection, several factors must be considered to ensure safe and compliant installation. Firstly, determine the load requirements of the circuit. This involves calculating the total current that the circuit will be expected to carry under normal operating conditions. This calculation should include considerations for both continuous and non-continuous loads. Secondly, select the appropriate conductor size based on the calculated load requirements and the allowable ampacity of the conductor. The ampacity of a conductor is the maximum current it can carry continuously without exceeding its temperature rating. Table 310.16 in the National Electrical Code provides ampacity ratings for various conductor sizes and insulation types. Factors such as ambient temperature, the number of conductors in a raceway or cable, and the presence of other heat sources can affect the ampacity of a conductor. Adjustments and corrections to the ampacity may be necessary to account for these factors. Thirdly, choose an overcurrent device, such as a circuit breaker or fuse, with a rating that is appropriate for the conductor size and the load requirements of the circuit. The overcurrent device is designed to protect the conductor from overloads and short circuits by interrupting the flow of current when it exceeds a predetermined level. NEC section 240.4b permits the use of the next highest standard overcurrent device rating in certain situations, but it is essential to understand the conditions under which this is allowed. Fourthly, ensure that all equipment used in the installation, including conductors, overcurrent devices, and terminals, are rated for the appropriate temperature. The temperature rating of a conductor or device indicates the maximum temperature at which it can operate safely. It is crucial to select equipment with temperature ratings that are compatible with the operating environment and the anticipated load conditions. Fifthly, consider the voltage drop in the circuit. Voltage drop occurs when the voltage at the load end of the circuit is lower than the voltage at the source end due to the resistance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. Sixthly, properly install and terminate all conductors and equipment in accordance with the manufacturer's instructions and the requirements of the NEC. Proper installation techniques are essential to ensure the safety and reliability of the electrical system. This includes using the correct tools and methods for stripping, splicing, and terminating conductors, as well as ensuring that all connections are tight and secure. Seventhly, label all circuits and equipment clearly and accurately. Proper labeling is essential for identifying circuits and equipment and for facilitating maintenance and troubleshooting. Labels should be durable and legible and should provide information such as the circuit number, the load served, and the overcurrent device rating. Eighthly, inspect and test the installation to verify that it meets all applicable requirements. Inspection and testing are essential for identifying any defects or deficiencies in the installation and for ensuring that it is safe and compliant. Testing should include continuity tests, insulation resistance tests, and voltage and current measurements. Ninthly, maintain accurate records of the installation, including drawings, specifications, and test results. Accurate records are essential for documenting the installation and for providing a basis for future maintenance and modifications. These records should be stored in a safe and accessible location and should be updated as necessary. Tenthly, stay up to date on the latest edition of the National Electrical Code and any applicable local codes and regulations. The electrical code is constantly evolving to reflect new technologies and safety practices. It is essential to stay informed about these changes to ensure that all installations are compliant and safe. By following these guidelines, electrical professionals can ensure that conductors and overcurrent protection are selected and installed correctly, minimizing the risk of electrical hazards and ensuring the safety and reliability of electrical systems. In specific scenarios, understanding the nuances of conductor ampacity and overcurrent protection is critical. For instance, when dealing with motor circuits, the NEC provides specific rules for selecting overcurrent devices and conductors to accommodate the motor's starting current. Motor starting current can be significantly higher than the motor's full load current, and the overcurrent device must be sized to allow the motor to start without tripping while still providing protection against overloads and short circuits. In such cases, the NEC permits the use of inverse time circuit breakers or fuses, which have a time delay characteristic that allows them to withstand the high starting current of the motor without tripping. Another scenario involves the use of conductors in high ambient temperature environments. As the ambient temperature increases, the ampacity of a conductor decreases. The NEC provides tables that specify the ampacity correction factors that must be applied to conductors in high ambient temperature environment. These correction factors reduce the allowable ampacity of the conductor to prevent it from overheating and potentially causing a fire. Similarly, when multiple conductors are installed in a raceway or cable, the ampacity of each conductor must be derated to account for the heat generated by the other conductors. The NEC provides tables that specify the ampacity adjustment factors that must be applied to conductors in these situations. These adjustment factors reduce the allowable ampacity of each conductor to prevent overheating. Furthermore, understanding the difference between conductors with different insulation types is essential. Conductors with higher temperature ratings, such as those with THHN or XHHW insulation, can carry more current than conductors with low temperature ratings, such as those with TW insulation. The NEC provides ampacity ratings for various conductor sizes and insulation types in Table 310.16. It is essential to select conductors with insulation types that are appropriate for the operating environment and the anticipated load conditions. When working with nonlinear loads, such as those found in electronic equipment and LED lighting, it is essential to consider the effects of harmonic currents in the electrical system. Harmonic currents can cause overheating of conductors and equipment, as well as voltage distortion and other problems. The NEC provides guidelines for mitigating the effects of harmonic currents, including the use of harmonic filters and the oversizing of conductors. In healthcare facilities, the NEC requires the use of isolated power systems in certain areas, such as operating rooms and critical care units. Isolated power systems are designed to prevent electrical shock hazards by isolating the electrical system from ground. These systems typically include an isolation transformer, a line isolation monitor, and special grounding requirements. In hazardous locations, such as those where flammable gases or vapors are present, the NEC requires the use of explosion-proof equipment and wiring methods. Explosion-proof equipment is designed to contain any internal explosions and prevent them from igniting the surrounding atmosphere. Special wiring methods, such as rigid metal conduit with threaded fittings, are required to maintain the integrity of the explosion-proof enclosure. When installing underground wiring, it is essential to consider the effects of soil conditions, moisture, and temperature on the conductors. The NEC provides guidelines for selecting conductors and wiring methods that are suitable for underground installations. These guidelines include requirements for burial depth, conduit type, and conductor insulation. In high-rise buildings, the NEC requires the use of special wiring methods and fire-stopping techniques to prevent the spread of fire from one floor to another. These requirements include the use of fire-rated cables, fire-stopping materials, and special conduit installations. When working with renewable energy systems, such as solar photovoltaic systems and wind turbines, it is essential to comply with the specific requirements of the NEC for these systems. These requirements include guidelines for conductor sizing, overcurrent protection, grounding, and disconnecting means. In industrial facilities, the NEC provides specific requirements for the installation of equipment and wiring in hazardous locations, such as those where flammable liquids or dust are present. These requirements include the use of explosion-proof equipment, intrinsically safe circuits, and special wiring methods. When working with medium-voltage systems, it is essential to follow the specific requirements of the NEC for these systems. These requirements include guidelines for conductor sizing, overcurrent protection, grounding, and disconnecting means. The NEC also provides requirements for the installation of surge protective devices to protect electrical equipment from voltage surges caused by lightning strikes or other transient events. Surge protective devices are designed to divert surge current to ground, preventing it from damaging sensitive electronic equipment. When working with flexible cords and cables, it is essential to select cords and cables that are suitable for the intended use and environment. The NEC provides guidelines for the use of flexible cords and cables, including requirements for conductor size, insulation type, and ampacity. It is also important to ensure that flexible cords and cables are properly supported and protected from damage. In agricultural buildings, the NEC provides specific requirements for the installation of equipment and wiring to protect against electrical hazards in wet and corrosive environments. These requirements include the use of corrosion-resistant materials, watertight enclosures, and special grounding methods. When working with temporary wiring, it is essential to follow the specific requirements of the NEC for temporary installations. These requirements include guidelines for conductor sizing, overcurrent protection, grounding, and disconnecting means. Temporary wiring must be removed as soon as the temporary need has passed. In educational facilities, the NEC requires the use of ground fault circuit interrupters, also known as GFCIs, in certain areas, such as bathrooms and kitchens, to protect against electrical shock hazards. GFCIs are designed to detect small ground faults and interrupt the flow of current, preventing electrical shock. When working with electric vehicle charging equipment, it is essential to comply with the specific requirements of the NEC for these systems. These requirements include guidelines for conductor sizing, overcurrent protection, grounding, and disconnecting means. It is also important to ensure that the charging equipment is compatible with the electric vehicle being charged. By understanding and applying these specific considerations, electrical professionals can ensure that conductors and overcurrent protection are selected and installed correctly in a wide range of applications, minimizing the risk of electrical hazards and ensuring the safety and reliability of electrical systems.